Hello everyone, please be welcome to a next episode of ChemiWorldClasses. Okay, actually today I am very happy because we are starting with a new section, right? So this section is called History of Chemistry, right? So this section is not only about, of course, of history, right? Because we are going to talk about different compounds, different substances, their historical development, and the most important, what is the application of these substances in the modern life, right? So here the question is how chemistry can make our life very different, right? Taking into consideration the past from now. Okay, in today's video, we are going to talk about the Prussian Blue. What is Prussian Blue? Prussian Blue, it's a very important compound because it was the first synthetic dye, in this case, of color blue. In this video, I am going to talk about the history, the properties, and the application of this important compound, right? If you like my videos, please subscribe, right? That would be very important for me because I would like to continue with this effort to bring in you chemistry in a simpler manner, right? If you're ready, let's begin. Welcome to ChemiWorldClasses. This is your channel, this is your space. Give me a like. Okay, let's ready. As I said, the Prussian Blue was the first synthetic dye in the history, right? In the modern history, this is quite important because actually the Egyptians, known from several time ago, they call Egyptian blue, right? So this is the first color, right? That it was synthetic. In this case, I am talking about, yes, the first synthetic dye, but in the modern history, right? What is the Prussian Blue? The Prussian Blue possesses this formula, actually, that you can see here. It seems very complex, but it isn't in reality. Later on, I am going to produce more videos in order to show you what are a coordination compound, right? Actually, Prussian Blue, it's a coordination compound, but what is that? It sounds very difficult, but it isn't so much. So this is a coordination compound. In a coordination compound, we have a metal atom that is surrounded by a series of, it can be atoms, molecules, that it can be neutral, positive, or even negative, right? That are going to call ligands, right? Those ligands are going to surround the metallic atom in a certain manner in order to form a coordination compound. In this case, the electrons that are forming the chemical bond come only from the ligands, right? And the metal will have empty spaces in order to accept these electrons coming from the ligands. In this case are not the spaces, right? Are orbitals. But what is the importance of making this video? Maybe you can ask me, right? The importance of the Prussian Blue is that on ancient times, actually, it was very difficult to produce the color blue, right? I am going to explain the reasons of this problem, right? In a moment in the video, right? But in this point, you need to have in mind that on ancient times, it was quite expensive to have a blue color in the paintings, right? For example, actually the blue color was considered the color of the royalty because it was so very, very expensive to have a blue color in paintings, right? So in this manner, actually, the Prussian Blue, because it was synthetic, right, opened the window to explore chemistry as a science capable to produce new and different colors, right, in order to use them in paintings, in arts, in clothing, etc., right? Actually, this is the importance of Prussian Blue. I am going to talk about the history of this compound. The discovery of Prussian Blue actually was serendipitous. What does that mean? Actually, that it was discovered by accident. The history of the discovery of this compound starts in the current Germany, actually. That's the reason why, because this compound it is called Prussian Blue, right? And it was in 1704. Actually, color artist maker, his name was Henrik Diesbach, was working in order to obtain a crimson lake, right? So he was in his laboratory mixing things and making some preparations, right? However, he realized that one ingredient was missing. That ingredient was known as potash. What is potash? Potash is the common name for potassium hydroxide. So what happened next? He decided to visit a local alchemist called Johann Conrad Dippel. Actually, this character lived in the Frankenstein castle. Ho, 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 ho. Johann Conrad Dippel was more or less famous because of the production of a miraculous product, right? Called animal oil. Actually, he produced this animal oil using some dead animal parts such as bones, flesh, etc., and blood, for example. So Johann Conrad Dippel actually prepared this elixir in order to treat some diseases and bring to the people health, right? So returning to the case of Henrik Diesbach, actually Henrik Diesbach came to visit Dippel in order to obtain potash. So actually Dippel gave him the potash that he wanted. Imagine what happened when actually Henrik Diesbach came back to his laboratory and continued working in the preparation of the Crimson Lake, and oh surprise, actually he didn't obtain a Crimson Lake. Instead of that, he obtained a dark navy blue color, right? Oops, how was that possible? Actually, the explanation that we have nowadays, and actually it was the explanation that Henrik Diesbach created in his head, it was that the potash was contaminated with some residues of this animal oil of Conrad Dippel, right? Nowadays, we already know actually that the animal oil was very rich in nitrogen compounds such as pyrols and alkyl cyanides, right? Alkyl cyanides. What is that? Actually, if you remember, this was the formula of the Prussian Blue, right? We have the Cn ion. What is that? We call that ion cyanide, right? In this case, actually cyanide comes from the Greek word cyanos, that means blue, despite the fact that most of the cyanide compounds are colorless. That was the importance of the Prussian Blue, in order to remark that having this ion, you can produce the Prussian Blue. Maybe you can think that in the moment Henrik Diesbach was very angry, but actually it doesn't, because as I said, during that time it was very difficult to produce the color blue, so it was fabulous, right? In this manner, actually you may think that the Prussian Blue discovery caught the attention of many people, right? However, it wasn't the case. Actually, the preparation of the Prussian Blue, starting from organic materials such as the animal oil, was kept secret for 20 years more. In 1724, John Woodward actually published a method in which he described the synthesis of the Prussian Blue via organic material, right, such as blood. Actually, this paper was published in Latin, and it was called the ox blood method. Oof. Actually, as you can imagine, it was not pleasant to prepare the Prussian blue using organic material, right? Instead of that, it will be very useful to produce the same ion or the same compound by inorganic materials in order for not working with stinky materials. During that time, actually, the chemistry was not so well founded, such as nowadays. So little by little, actually, the chemists and some science made some discoveries that actually promote the use of inorganic materials in order to produce Prussian blue. So one of these contributions actually came in 1782 when Carl Wilhelm Scheele, a German chemist, actually discovered the prussic acid, right? So what is the prussic acid? Actually, this is called the hydrocyanic acid. Actually, he was very lucky because he was heating Prussian blue in presence of sulfuric acid in order to produce this lethal compound. It's very toxic, right? Actually, most of the compounds having the cyanide ion are very toxic because actually the cyanide can replace the molecule oxygen inside the hemoglobin, right? So some years later, actually in 1814, Joseph Guy Lussac was capable to isolate and synthesize the cyanogen, that it has this formula, right, in which you have two cyanide ions together. So in this manner, the inorganic synthesis actually was possible with several advantages, such as the possibility of working with more or less not stable, but some compounds in which you can control the quality and the purity instead of working with organic materials, right? And this was very important because actually it opens the possibility to synthesize new pigments, new dyes, and colors that it could be useful in chemistry and in art and in general in many aspects of our lives. Okay, let's start. As I said, Prussian blue, it's a coordination compound. Here you have again the formula. What is its name? Its name, according to chemistry, it's ferrous ferricyanide, right? Or you can call it more properly hexacyano ferrate 3 of iron 2, right? Oh my God, what is that? It sounds very difficult, but it isn't, right? Now let's talk about the chemical properties of Prussian blue. Actually, we can distinguish between two kinds of Prussian blue. This is the first one. This compound is called insoluble Prussian blue. And we may have also another kind of compound that it's called soluble Prussian blue with this structure. But wait a minute. Actually, they are not, both of them, actually they are not really soluble. Instead of that, actually they form dispersions, right? So dispersion is when you have some particles, right? And they are not properly solubilized. Instead of that, they are dispersed, actually, in another media. In the case of Prussian blue, we are going to form what we call a sol. What is a sol? It's a dispersion of a solid into a liquid, that in this case, it's water most of the times. Another interesting characteristic of the Prussian blue is its density, that it's quite low in comparison with the other iron compounds. The density of Prussian blue is only about 1.8 grams per cubic centimeter. So how can we explain that this density actually is very small in comparison with the other compounds? Because of its crystal structure, right? So Prussian blue possesses crystal structure. Here you have it. And this crystal structure is full of empty spaces, right? So inside this structure you are going to have some kind of holes, right, in which you can accommodate very easily some ions. You may have a question in this moment, right? Why does the Prussian blue possess that very beautiful color? And the answer in terms of chemistry is because we have a mixed balance compound. What does that mean? That means that in the formula we are going to have iron in two different oxidation states. So if you remember, the atoms are composed of protons, neutrons, and electrons, right? In the center of the atoms we have a nucleus, and around the nucleus we may have some electrons orbiting around it, right? So sometimes you can provoke some jumps from those electrons from a low energy level to a high energy level. In the case of Prussian blue, actually these transitions occurs at 680 nanometers, right? That actually provokes the blue color. This transition goes from the iron 2 ion to the iron 3 ion in the formula. That's the reason why, because we can observe the Prussian blue with this color. Prussian blue is what we call an electrochromic compound. So what is that? An electrochromic compound, it's a compound who has a different color, or a compound that it can change from a color to another depending on the oxidation state it has. So in this manner, of course, the Prussian blue is blue, but we can oxidize, that is to retire electrons, from the iron 2 atom in order to have all the iron with the 3+ oxidation state, such as in this formula. So this is what we call the yellow Prussian, right? Or the Prussian yellow. On the other hand, we can do the opposite process and reduce all the iron in order to have this compound that is called the Berlin white, in which actually all the iron atoms possess the 2+ oxidation state. Actually, Prussian blue, with this property of a crystal lattice with so many empty spaces, can be used in several applications. One of them, it was for treating the thallium poisoning. What happened in this case? In some military regimes, actually during the last century, it was a very common practice to supply some thallium doses to the enemies of the government, for example, right? Actually, thallium was a very discreet poison because actually the symptoms can be confused with another diseases. However, thallium plus, that is this ion, possesses a radius of 164 picometers that actually can enter and replace the potassium ions in the crystal lattice, for example. So you can supply with Prussian blue pellets, because actually Prussian blue it's quite inoffensive to the system, and use it as an antidote, right, against the thallium poisoning. Another ion, right, that actually can enter into the crystal lattice of Prussian blue, it's cesium, right? Cesium, it's another element of the periodic table, This is not a particularly risky element, right? However, there is a radioisotope that it's called cesium-137 that it's quite dangerous. So maybe you can think, how can I be in contact with these radioisotopes? Actually, as you know, in 1986, there was a nuclear accident in Ukraine that it was in a location called Chernobyl. Actually, this accident was enormous, and there was an emission of a toxic cloud all over Europe. So actually, cesium-137 was present in that toxic cloud. The problem with this toxic cloud, it was that it can be settled or deposited into the grass. And actually, some animals that can eat grass, such as the sheep, can be contaminated with this radioisotope. And actually, the contamination with this radioisotope, it's very serious, because actually it can pass from the different levels in the food chain. So maybe you can eat this meat that is contaminated with cesium-137, and you can get contaminated, right? So that was a very big problem during the last century. Actually, in 1992, it was discovered that some herds of reindeers that eat so many lichens, and especially mushrooms, in its diet were contaminated, with these radioisotopes, cesium-137. Actually, what was the solution? The solution was to supply some small quantities of Prussian Blue in the salt stocks, in order to provide that the reindeer cannot be contaminated with this cesium-137. Now we are going to return to the central point in this video, that is the relationship between chemistry and other disciplines such as arts. As I said, having the blue color was particularly difficult in ancient times, because it was too expensive to extract and, for example, to mine some minerals containing this very beautiful color. But actually, that doesn't mean that we don't have options. Yes, we have it. One of them was indigo, but the problem with this pigment, it was that he was very prone to fading, right? Another option was the ultramarine, that it was obtained from a mineral called lapis lazuli. However, it can be only obtained in some mines in Afghanistan, right? So you can imagine how difficult it was to mine and actually to transport on ancient times this material, right? So it was very, very expensive. So in this manner, Prussian blue appears initially, I need to say only initially, as a good option in order to substitute these pigments. However, there is a problem with Prussian blue. Aww. What is that problem? That the color provided for the Prussian blue was more or less unstable with some ingredients, such as, for example, the alkalis. In this case, the color blue in Prussian blue fades when you add some compounds called hydroxides that are basic compounds. So actually, it is not possible to use Prussian blue in some preparations or in some paintings in the technique al fresco. When you use lime, that it has this formula, in the normal technique. The second disadvantage of Prussian blue in masterpieces was the photosensibility factor, right? What is that word, photosensibility? Actually, there are some substances, such as Prussian Blue, that can be fading light in several extents or in several degrees, right? That was another problem that limits the use of Prussian Blue in arts. However, I have very good news for you. Actually, the Prussian Blue permits to develop a technique that it's called cyanotypes. So what is a cyanotype? Actually, cyanotype is the ancestor of the modern photography. I am not talking about the photography of nowadays, in which you have some digital devices such as your cell phone or your tablet, and you may have some photographs, right? So I am talking about the photography in paper. So let me explain what is a cyanotype. This phenomenon was firstly described by William Herschel. William Herschel was an astronomer, and actually he was the son of the discoverer of the planet Uranus. Okay, the idea was that William Herschel was trying to devise a new photographic method because he observed that some organic dyes obtained from some plants in his garden can be bleached using sunlight. So he was trying to develop a photography process using this phenomenon. However, he found that the exposition times were very long. That is to say, the time in which you need to expose the paper, for example, in order to make a photography, was very, very long. So the solution to this problem actually came from a friend of him. His name was Alfred Smith. Alfred Smith was a colleague in the Royal Society. He was a chemist, and he provided Herschel with a compound. This compound was potassium ferricyanide with this formula that you have here. The potassium ferricyanide actually it's a compound with very brilliant orange and beautiful crystals, right? So actually this compound proved to be more sensitive to sunlight bleaching. So imagine, actually Herschel was very happy because he was able to reduce the exposition times. Actually, those were the first step for the photography development. After some time, the same Alfred Smith provided to Herschel another more sensitive compound, that is the iron ammonium citrate, right? Actually, this compound is still used nowadays in order to make cyanotypes. Of course, it is evident that cyanotypes are not used so frequently anymore, right? Because we have modern photographic techniques. However, it established the basis of the modern photography. So that was important of the Prussian Blue. In the case of cyanotypes, so you may have these very beautiful blue and white designs, and I promise you that we will have a video in which I am going to show you how can you do cyanotypes at home in order to make some photographs and designs. Okay, and that's all for my part. Welcome again to ChemiWorldClasses. I hope you really enjoyed this video. If you like it, please click the like button and subscribe. And please don't forget that if you have comments, questions, or doubts with homeworks, preparation for exams, projects, so you can email me at ChemiWorldClasses@gmail.com, and please do not hesitate to contact me. I would gladly help you with online tutoring. If you like it, so you can subscribe also to my Spanish channel that it's called Chemimundo, in which you can find the same information that in this channel, but in Spanish. Thanks for watching. It was a pleasure. Thank you for being here in ChemiWorld. This is your channel. This is your space. Click the like button. See you next time.